Today we will be talking about the Cartesian equation of a line. This seems quite a familiar topic to us. Let's see our approach to the Cartesian equation of a line starting from our discussion on vectors. Okay, so here I have the Cartesian plane, and I would like to write the Cartesian plane of this random line L. That's a random line whose Cartesian equation I would like to find. Look what my approach is going to be. I am going to build, this is something new, I'm going to build a so-called normal axis. Normal axis. Which is nothing else but a line perpendicular to my line L. This is a very important observation. The normal axis and my line are perpendicular lines. So the blue line is called the normal axis. Okay, I'm gonna take a random point whose coordinates are A and B. Now, I constructed a vector, a position vector n, that can be written on components as A and B. Good. Next thing that I'm going to do, I'm going to consider a certain point, P0, of coordinates x0, y0, on my line L. That is a fixed, that doesn't mean, it's a given point on the line, P0 of coordinates x0, y0. Then I'm going to consider another random point, P, of coordinates x and y. P is the random point that will determine the equation of the line. P can be anywhere on the line. As I move P along my line, P will determine my equation of the line. Oh, so let's place it somewhere over there. Good. Let's construct together the vector P0P. Let's do that. P0P is, by definition, using position vectors, OP minus OP0. So P0P can be written as OP is xy minus x0y0. So it's gonna be P0P x minus x0, y minus y0. Good. So that is a vector P0P. Now let's try to see how it looks. P0P is this vector over here, right here. So it's P0P, there you go. That is a vector I'm talking about. Of course, it's given as a position vector, so it should be right here. That is as a vector P0P as a position vector. Good. So now, what do I know about the following two vectors? P0P and the normal vector n. What do I know about them? They are perpendicular. The angle in between is 90 degrees. Okay, as a result, I can write something very interesting that I know about the perpendicular vectors. Their dot product is 0. The dot product of those two vectors is 0. Okay, so let's write that. The dot product of x minus x0, y minus y0, and what's the second one? N is AB must be 0. Let's do a little bit of algebra. Definition of dot product is A times x minus x0 plus b times y minus y0 must be equal to 0. Let's expand. Ax minus ax0 plus by minus by0 equals to 0. Or, in other words, I'm going to reorder a little bit. Ax plus by minus ax0 minus by0 equals 0. Please notice that a, b, x0, y0 are all constants. They are constants, right? I'm gonna rename negative ax0 minus by0. I'm gonna rename this as c. As a result, c is a constant. I can rewrite the equation of a line as ax plus by plus c equals 0. Does it sound familiar? Of course it is. It's a grade 9 Cartesian equation of a line. But the new and interesting thing is that A and B are nothing else but the components of a normal vector, which is extremely, extremely important to me. Good. Let's see how we are doing. We are doing okay. We still have time to have some discussions. Good. Let's move on. Let's talk a little bit about parallel lines. What is parallel lines? The condition for two lines to be parallel in terms of their normal vectors. Normal vectors. What can we say about that? Well, first of all, let's draw their normal vectors. One is something like that. Is it perpendicular to line L1? Sure. This is line L1, this is line L2. Let's do the second one. Second one, perpendicular. What can you tell me about these two vectors? They are collinear, right? The two normal vectors must be collinear in order for L1 and L2 to be parallel. So L1 is parallel to L2 if and only if the two normal vectors, this is normal vector, let's change the color of the second one, okay? Normal vector 1, this is normal vector 1, and this is normal vector 2. The condition must be normal vector 1 is, well, almost the same as normal vector 2, but times a scalar k. To change the direction and the magnitude, of course. But the two vectors are collinear, as you can see. Okay, so the condition for two lines to be parallel is that, and one, the normal vectors must satisfy a relation that you see right here. Good. Now, let's try to do the same thing about two perpendicular lines. I am giving you two perpendicular lines, L1 and L2. Let's make them, they don't really look perpendicular. Do they look more perpendicular now? Yes. Again, I want a condition for L1 to be perpendicular on L2 in terms of their normal vector. So first thing that we're going to do, we're going to construct this normal vector. So I have my first normal vector is this one. My second normal vector is this one over here. Okay, good. Change the color of this one. I can't. Why? It doesn't why. Maybe this one. Yeah, this is better. Good. So don't forget what I want. I want the condition for L1 and L2 to be perpendicular. Guess what's going to happen with their normal vectors, N1 and N2? They will be perpendicular as well. How do I write the fact that two vectors are perpendicular? The dot product of these two vectors must be 0. So there you go. This is a condition for two lines to be perpendicular in terms of the normal vectors. Okay, so that's it for today. 10 minutes.